Okay. Can you hear me? Yeah. So welcome everyone. I'm Michael Reynal. I work at Bootlin, formerly Free Electrons. Just before starting, who knows Free Electrons, at least, or use its services? Okay. So we are renaming the company because of a legal dispute. If you want more information, you can go to check our website, bootlin.com. Otherwise, it's exactly the same. We are just renaming it. Same people inside, same purpose, sharing and contributing. On my side, I work a lot. I contributed quite a lot to the NAND subsystem the last months, and sometimes I contribute also on Armada SoCs. So this talk is about NAND flash memories. Initially, I wanted to talk about the Linux stack mainly, but while I was writing the slides, I found it was kind of boring to spend an hour on that. So I added a first introduction on the physical part, how it works actually physically. And I will talk mostly about, at the end of the talk, I will spend some time on the execop interface, which is a new one which is currently being added in the Linux kernel to do some low-level stuff. I'm not a NAND expert. If you disagree with me, please go talk to Boris Brazilian, the NAND maintainer, which is in this room. I will probably simplify some aspects on the electrical part. I won't talk about NOR flashes at all, just NAND flashes, and especially SLC NAND, which stands for single level cell. It's when you have only 1 bit per memory cell. It's for simplifying the explanations. Okay, before starting the technical part, just some commercial information. NAND was supposed to replace hard disk drives. The main goal was to have the lowest cost per bit. We'll see how they achieved that with the design, the hardware design. And you can find them in a lot of flavors. I will talk about raw NANDs and how you drive them with a NAND controller, but you can also find them on SPI buses. And there are a lot of more and more managed NANDs under the form of eMMCs, SSD, USB sticks, and so on. So yeah, first let's build our NAND cell, our NAND memory cell. I will start very deep into the matter with the silicon atom. There is a nucleus with 14 protons and around it 14 electrons. It makes it electrically neutral. This is very important. On the last orbit, there are 4 valence electrons. It's called the valence shell. For each electron will bond with another electron of another silicon atom, and it will make the crystal. In a perfect world at 0 Kelvin, absolute 0, you won't have any current with silicon. It's almost an insulator, but at 20 degrees, 20 Celsius degrees, you have you get energy from, for instance, the light, and if light strikes an electron, it will jump into the other upper orbit with much more energy, and this is a free electron which can carry electricity. Of course, if you don't apply any voltage, it will just drift randomly until it loses its energy and combine back into the whole it created. So to make use of silicon and make them more conductive, people invented doping. And the purpose of doping is adding impurities in the silicon crystal. And these impurities are atoms that have one more or one less electrons on their valence shell. So doing that, you put another atom in place of a silicon atom. It will bind, let's say, with 4 other silicon atoms with its 4 electrons on the valence shell. But 1 electron will remain and won't bond with any other atom. And this is a free electron. It can carry electricity. If you add more electrons, it's n-doping. Of course, if you have 3 electrons instead of 4 on the valence shell, it's p-doping for positive. You have a hole, it's actually a lack of electrons. Okay, let's put 2 differently doped areas together. You make a p-n junction. The electrons close to the junction will, on the n side, will jump over the junction and combine into holes on the p side. It makes both regions not electrically neutral, and one will be positive in the n side and one will be negative on the p side, because matter was electrically neutral, is electrically neutral, but you added electrons on a side which was already neutral. So there are more electrons than protons in this area, and it makes it negative. It creates an electric field here, a barrier that is hard to cross for other electrons on this side that cannot combine with other holes on the p side. So you don't have, Let's apply a voltage on it. Electrons, if you apply a plus voltage on the n side, electrons will be attracted, but you won't have any current actually. But if you apply the plus voltage on the p side, electrons that were close to the junction will jump from hole to hole until they get out of the circuit, while other electrons on the n side will be able to jump across the barrier, and this will imply a current. Let's have now what we call a MOSFET. It's 2 n regions separated by a p region. Okay. MOSFET is a metal oxide semiconductor field effect transistor. So metal oxide semiconductor is actually this part. The leg in the middle is called the gate. It's metal. Okay. It's separated from the p substrate, which is also called the bulk, by an oxide, which is an insulator. So there you can have actual electricity, electrons moving from here to here. If you apply a voltage across the external legs, it's the first case we had before with the p-n junction, you won't have any current. If you also apply a plus voltage on the gate, you will have positive charges here on the gate that will attract electrons and create a small channel, so electrons could go from one n side to the other one, and this creates a current. So this is the basic of transistor. We all agree that here we cannot store data yet. And what we want to build is a memory cell. So people added what we call a floating gate here. The floating gate is separated from the other parts with an insulator. Okay. So there is no current going through it. And same as before, if you apply a voltage across the external legs and a positive voltage on the gate, you will still have your charges there that will attract electrons and create this channel. Same as before, then you have a current flowing. But if you have electrons in the floating gate in the center here, holes are not repelled anymore and instead are attracted here, and it makes the jump too high for the electrons in the n regions. So there you can't have any more current, even if you apply a plus voltage on the gate. And that's how you store a zero, a logic 0. The previous condition was a logic 1, when there was current. So the question is, how do we put electrons in the floating gate? We do that with what we call the Fowler-Nodheim tunneling effect. It's quantum mechanics. Basically, you will apply a high positive voltage on the gate, much higher than before. So electrons will be attracted and will tunnel through the oxide layer, because they are attracted here by all the positive charges on the gate. This region, this oxide is a bit thicker than this one, so electrons could tunnel through this one, but not through this one. Otherwise, you wouldn't have any charges stored. So this is called programming a cell to a 0 state, because once you have electrons there, you can't have any more current there. In the other way around, if you want to raise the cell, you have to apply a high negative voltage on the gate. So putting a lot of electrons on the gate, repealing all the electrons in the floating gate back into the substrate. This is my MOSFET, actually my floating gate transistor, but the figure is just much simpler. You still have the floating gate here. This was the gate, also called the word line, we'll see why. And both external legs are called the bit line. If we put two cells like that in series, well, we are supposed to have two NPN regions side by side, but what we do to gain space is to have only one region between them. And when you create your chip, you just have to put N regions regularly on a P substrate, and that's all. And you get your NPN regions. It makes the layout very, very thin, and that's why you can have a lot of memory cells on a small area. Just a side note, imagine you apply a voltage across both transistors. If you want to get a logic 0 on this spot, you'll have to apply a logical 1 on both gates to make both transistors passing and have the 0 here. And this is the NAND gate. This explains the name of the technology. Okay, we've created one cell. Now we want a bit more than only one bit in our chip, so we put them in series. This is a string of cells. We can put as much cell as we want in series, but you know, if you want the current to be passing through the transistors, when it's about silicon, it's about 0.7 volts. So we limit ourselves to 32 to 64 cells on strings in series. After, it would be too much for embedded system, for instance. So if you want to read the value of one cell inside the string, you have to apply a positive voltage on the gate, as we've seen before. But if other transistors are not passing, you won't have anything, you won't have any current on this string, okay? So what you have to do is to add an even higher voltage on all the other gates of the other cells in the same string. So the other ones are forced to be passing. This voltage cannot be too high, or you will have the tunneling effect. Okay, now you can feel how fragile this design may be. So this is a string, but you can put a lot of strings in parallel. It makes a block. And as I told you earlier, the gate is now called the word line, because all the gates are connected together and are making what we call a page. If you are used to deal with NAND flash, a block, a page are terms that you usually meet. And when you want to select, let's say you want to program this cell, actually by selecting this cell and applying a high voltage on this gate, you will actually select all the cells in that string, in that page actually. And that's why you can only program and read entire pages at a time with NAND flash. If I go back a few slides, you remember when I talked about erasing the cells by moving out the electrons from the floating gate. Actually, I told you we could apply a high negative voltage on the gate, but high negative voltage are not as easy to obtain. So what we do instead is applying a high positive voltage on the bulk, on the P substrate. That has the exact same effect of attracting electrons out of the floating gate. One difference, a big difference. The bulk is shared across all the cells in one block. So when you want to erase a cell, you actually have to erase the whole block. And that's why we call that flash memory, because it's highly parallelized. A few words about bit flips. It's when you expect one logical value and actually you get another one. Cells, the Fowler-Nordheim effect, it's quantum mechanics. So yeah, it's stochastically distributed. It means hazards come into the equation, and you cannot actually know exactly how much electrons you will have in your floating gate. Otherwise, there are other effects. Cell might not be fully erased or programmed. For instance, electrons that tunnel through the oxide layer might not cross the entire oxide if they don't get enough energy and get trapped into the insulator. It makes regions of the insulator electrically negative and prevents other electrons from tunneling through that barrier. Also, there is data retention. It's when you store data in one cell, you put your NAND away for months or years, maybe 10 years. You get it back, and when you look at the data in it, some cells that were programmed to 0 are actually 1, because the electrons, when they tunnel through the oxide layer, they collide with material and damage it a bit. So the insulator might not be an insulator completely fine anymore. And with time, electrons can get out of it. And also there are read-write disturbances. When you read and write pages, you apply voltages across the cells just next to other pages, and yeah, it creates disturbances. For an SLC NAND, it's about 100,000 program and erase cycles. For MLC, for instance, it's much less than that. I haven't talked about MLC. It's a multi-level cell when you put multiple bytes in one memory cell. But it's not very, very stable. So, okay. We now know how NAND flash is built. We have our NAND chip, and we now want to drive it. I'm still talking only about parallel NANDs. You'll have to wire it to your NAND controller. This is defined in some NAND protocol. There are NAND specifications for that. And I will explain briefly the logic here. You have an I/O bus. Okay, it's 8-bit wide or 16-bit wide, and a few logic lines. For instance, CE stands for chip enable. The NAND controller, the host, will assert this line when it wants to talk to a particular NAND chip. Actually, the This is for enabling one die. You may have multiple dies in one chip, but I will simplify this, and let's say we have only one die in this chip. The ready buzzy pin works in the other way around. The NAND chip can assert and deassert it to indicate that it's buzzy and it cannot do another operation. Write protect, WP, is to let the NAND chip know that it cannot accept neither write operations nor erase operations. And I will get back right after for these lines. First, I want to show you the NAND protocol, how it works. Basically, there are three possible cycles that can happen on the bus: command cycles, address cycles, and data cycles. And you can have wait periods. It's when the ready buzzy pin is actually deasserted by the NAND chip. So when a command cycle is asserted on the bus, the NAND chip knows that it's a command because the command latch enable pin is also asserted. Same happens for the address latch enable pin, and read enable, write enable are for data when the NAND controller is the master of the bus or when the NAND chip is the master of the bus. Yeah, of course, when controller address are asserted on the bus, it's always a write, and it's always this one that is asserted because the NAND controller is the master. So when you put together command, address, data, and wait cycles that are NAND instructions, you get a full NAND operation. So let's say how it looks, a real NAND operation. My first example is how to do a read page. You have to send the 0 byte, which is a command to tell the NAND chip we're going to do a read operation. Then a few address cycles, okay, where I want to read. Then the 30 command, which means, okay, now you can bring the data. There the NAND chip will tell the host he is retrieving the data and he has to wait a bit. And then a few data cycles, depending on how much data you asked for. Some commands are a bit less complicated. For instance, the reset one, it's just the FF command, 1 byte, and then the chip will reset itself and deassert the ready buzzy pin the time it's buzzy. Controllers are often embedded in SoCs. There are diverse implementations of them. Some are really simple. Others are quite complicated. I'm going to talk about that a bit later. Its main job is just to communicate with the NAND chip. It can embed more logic, for instance. It can handle, it can have an ECC engine. ECC is for error correcting code, yes, to handle bit flips in the pages, or advanced logic to enhance the throughput. So now we know how the electrical part works, what it is to talk to a NAND chip with a NAND protocol. So let's see how it's done in Linux. This is the MTD stack. MTD stands for Mass Technology Device. When you want to interact with your NAND chip, you will pass through these layers. So some of you may know the UBI, UBIFS layers. I'm not going to talk about them. It's a bit out of scope. The MTD layer is an abstraction level. From here, you don't know exactly what it's inside, if it's NAND or another technology. You'll go through the NAND core, which is the framework where all the logic must be. And the NAND core will make some orders to the controller driver that will drive actually the NAND controller. Okay? In terms of software, I don't know if you can see, it's a bit blurry, I'm sorry. Let's say you want to make a read on the NAND device. You will, from the user space, you will use the /dev/mtdx device. It will go through the mtd layer, okay? And the NAND core will first use the command func hook, which is supposed to be in the NAND core. It was actually at the beginning. This hook will send, will call the command control hook from the controller driver with either command or address cycles, one at a time. Then it can make wait periods with wait func and dev ready. There are other hooks implemented in the controller driver. And we'll retrieve or write data with the read-write byte word buff hooks that are also in the controller driver. But yeah, this is the linear view of the functions that are called. This has some limitations now. I guess when command func was first introduced in the kernel, it was perfectly fine to do things like that. But today, controllers tend to be more complex, and some of them actually need to do the whole operation at one time and cannot do such fine-grained instructions. For instance, sending just a command cycle, just an address cycle, and so on. So people started re-implementing the command func hook from their controller driver. So this was overloaded here. Problem is command func doesn't embed the data length you have to retrieve or to write. So some prediction started being done from the non-controller drivers. And it means the non-core wasn't fitting the need anymore. Also, because all the implementations were really different, when a vendor had a new operation, if you want to support this operation in the non-core, you have to patch all the controller drivers one by one. It's a lot of pain to maintain. And yeah, because developers started to implement only minimal set of commands just to make their own situation work. Yeah, it was incomplete. So to address these limitations, we decided to add another hook in Linux called execop, which is just a translation into NAND operation of what the MTD core wants to achieve. The NAND core will actually call the implementation of execop from the controller driver, giving him an array of all the instructions he wants to execute to do one NAND operation. I'm going to detail that. It should enter 4.16 in a few weeks. And the first driver that has been migrated to use this interface is the Marvel NAND controller. And others are coming. If you want to see a very simple implementation, you can have a look. I've sent some patches for the FSMC driver. It's really simple. Other drivers or the controller drivers are going to be merged, are going to be migrated anytime soon, I hope. So yeah, what do you have to do in the execop implementation from the controller driver side? You will receive an array of the instructions. First, you have to parse the sequence and split it in as much sub-operation as needed. If you think your controller won't handle this operation, you have to return an error. And this is another difference with the command func approach. where no error code was returned if the operation couldn't be handled. This way, the NAND core will be able to maybe try another way. There are multiple ways to do the same thing with NAND, and the NAND core will be able to try with another operation to do the same thing, even if the throughput is a bit. If you lose a bit of throughput. So yeah, for simple controllers, when you can split the operation in just the instructions, it's quite simple. You can do it by hand. Otherwise, we've introduced a parser in the core. So now, when you want to do, let's say, a read, the main read operation in the NAND core will now call the execop hook from the controller driver. And if the implementation is a bit complicated, you can just call the parser from the NAND framework, giving him an array of supported patterns. Each supported pattern has a callback, and the parser will go through the patterns, and whenever it finds one that fits the needs of the desired operation, it will call the callback with just the sub-operation that matches. This is an example of what an array of supported patterns can be. It's a bit simplified, of course, just for the example. Okay, the first pattern is one command cycle up to 5 address cycles, and maybe, if you need it, you can do also up to 1024 data cycles. The numbers here are actually the maximum number of this kind of cycle that you can achieve, because there are some limitations for that in the current controllers. The second one can either do assert a command cycle or a wait cycle or both. And the last one can just do some data transfers. If I go back to my first examples, the reset operation, which was a command cycle and then a wait period, well, the NAND parser will find that the second pattern actually matches that and will execute this callback, and that's all. For instance, if you want to do a read ID, it's one command cycle, one address cycle, and let's say 6 data cycles. The first pattern matches, even if the number of cycles are not the same. It's not a problem at all, and the first callback will be run. For the last example, the third one, the change read column, you want to assert a command cycle, then 2 address cycle, and another command cycle before reading data. This cannot be handled by any of the patterns here. So you'll have to split it into sub-operations. That is done by the parser automatically. And for instance, it will find that the 3 first cycles can be handled by the first pattern. So we'll call this callback with a sub-operation that matches only these 3 cycles. Then you want a command cycle, so the second pattern can do that, just one command. And finally, you want data cycles that the third pattern can handle. So this callback will be called, but this time it will be called twice because you can only handle 1024 bytes at a time, and 2000 were requested. So yeah, that's how it works. And what you should implement in your controller driver is this array and these callbacks. Of course, in the NAND core, there are other hooks. The most important for me was the execop one. But of course, you have to deal with other ones. I want to speak a little bit about the setup data interface hook. This one, data interface, is for timings. Maybe you know NAND timings can be of, you have different speeds. The ONFIS specifications has 6 of them. The slowest one, the mode 0, is supported by all the NAND chips, should be supported by all the NAND chips. But let's say you want to achieve highest throughput, you will have to set you will have to use let's say mode 4 or 5 that are really really fast. But for this, some tweaking, some configuration has to be done on the controller side, and this is handled by the setup data interface. So you give a data interface, and first the controller driver will have to return if yes or no it can be handled by this controller, and if it can, it will have to configure the controller to use this kind of timing for this chip. And when I say this chip, it's actually you can select the chip with this hook, and each time you'll have to switch from one NAND chip to another one if your design is like this. You'll have to switch from one timing mode to the other one, and this is done in the select chip. Also, even if the name is confusing, you actually select a die, not the entire chip. Some good habits. Yeah. When you hack into the NAND core, you should test. Of course, you should test, but you should use probably these binaries. They are from the MTD utils package. I use them a lot. If you are lost, I would say you can get the documentation, but actually this is a joke because there is almost none. But instead, you should ping the MTD community. There are a lot of people there that can help you. And please do not forget to put the NAND maintainers in copy. It puts them in a quite bad mood. And I work besides one of them. If you want more information, you can check the presentation of Boris Brazilian. Yeah, him. He made a talk at ELCE in 2016 in Berlin about the NAND framework, something more general, and also about the physical part of NAND flashes. I would suggest you to have a look at the Arnout van der Kapel talk at the same conference. Yeah, that's all. If you have any questions, I will be pleased to answer them. Thank you for your attention. The question is about the future of raw NAND. And yeah, it was kind of announced that raw NANDs will disappear and be replaced by eMMCs. And it's slowly happening, but we face the fact that a lot of people are still using raw NANDs, and there is still some work to do on this side. But yeah, probably in the next years, the market share of raw NANDs will decrease. Yes? About SPI-NAND, I can't answer you on that, but you can you can ask on the mailing list. Yes, or maybe. Yeah, you can come and talk to us at the end, maybe. Yes? Yeah? Some work has already been done to support. Oh, sorry. The question is about the support of MLC NAND and how this could be used to handle MLC, right? Actually, some work has been done about supporting MLC NAND in the Linux kernel. It's a bit more complicated than just knowing that there are multiple bits in one cell, because you have limitations on the fact that you cannot write pages in the order you want. There are a lot of problematics around that, and work has been done, but it's not upstream yet, and we lack some time to work on it. I think there was a last question there. No?
Do you know any other subsystems that use a similar mechanism with the command queue in it?
If I know other systems that use this kind of mechanism, actually I'm pretty new to Linux, so no. I have to be honest. Okay. If you still have any question, you can catch me in FOSDEM today. Otherwise, thank you very much.